Module 3, Lecture B, Joins and Reshaping. By the end of this lecture, you will be able to implement Polars joins that replicate common Pandas merge and join patterns across multiple tables. Apply Polars reshaping operations such as pivot and melt to reproduce Pandas pivot table and stack or unstack behavior. And design an end-to-end Polars pipeline that combines joins and reshaping to match the output of an existing Pandas workflow. Core join techniques. Core join types. In Polars, joins work similarly to those in other data libraries with several common types you should know. An inner join keeps only rows where the key appears in both tables, which is useful when you want the intersection of two datasets. A left join keeps all rows from the left table and adds matching information from the right table, so you preserve your main dataset while enriching it with extra details when available. A right join is the mirror image, keeping all rows from the right table, and in practice, you can think of it as performing a left join after swapping which table is considered left and right. In Polars, a full outer join keeps all rows from both tables, matching them where keys align and filling in missing values where they do not. This type of join is useful when neither dataset is primary, such as combining records from two departments to compare overlaps and differences. For example, merging regional sales systems with different customer lists reveals both shared and unique customers, which helps reconcile records. Choosing an outer join emphasizes completeness, accepting gaps in the data so that no potentially important information is discarded. In Polars, semi and anti-joins are used to filter rows based on whether key values match between tables without adding extra columns. A semi-join keeps rows from one table only when a matching key exists in the other, which is useful for narrowing a dataset to relevant records. An anti-join does the opposite, returning only rows with no matching key, which helps reveal gaps or missing information. Learning how these joins work alongside inner, left, right, and outer joins gives you precise control over how tables are combined and how complex merge behavior is handled. Python code. Core join types. This lesson should briefly demonstrate the main join types in Polars using very small, easy-to-read example tables. Focus on clearly showing how inner, left, outer, semi, and anti-joins differ in terms of which rows they keep from each table. The goal is to keep the examples compact and beginner-friendly, so learners can quickly see how each join behaves without being overwhelmed. By comparing these core join types side by side, students can build an intuitive understanding of when to use each one. This line tells you to install the Polars library if you are not working in a Colab environment. Polars is a high-performance library for working with data in table form, similar to Pandas. Installing it, make sure you have the tools needed to run the upcoming examples. Those examples will show how to perform different types of joins using Polars. We begin by importing the Polars library, which is built for fast and efficient work with data tables called DataFrames. It is similar to the Pandas library, but is optimized for high performance, especially with large datasets or complex operations. By bringing Polars into our script, we can create, modify, and join data frames efficiently. These capabilities are essential for the data processing tasks we will carry out in this code. We begin by creating a customer table as a data frame using the Polars library, which is similar to Pandas, but designed for higher performance. Each row represents a customer and includes a unique customer ID along with the customer's name. In this example, the IDs 1, 2, and 3 correspond to Alice, Bob, and Carol. Organizing the data this way makes it straightforward to join this customer table with other tables later by matching on the customer ID column. We create a data frame called orders using the Polars library to store customer identifiers and their order totals in US dollars. In this example, the customers have identifiers 2, 3, and 4, with order totals of 50, 75, and 20. This simple setup is used to demonstrate how join operations work when some customer entries match and others do not match entries in another table. We begin by printing the customer's table so we have a clear reference for the data we are about to use. Seeing the current state of the customer's data helps us understand the context before we perform any join operations. The printed output shows each customer's identifier along with their name, which will be important when we later combine this table with other data. We first display the orders table to give context for the join operations that follow. Seeing the original structure and values helps us understand what the data looks like before any changes are made. This printed table serves as a clear reference point, so we can more easily see how each join operation modifies or combines the data. In this example, we use the Polars library to perform an inner join on two data tables, customers and orders, based on their shared customer ID column. An inner join keeps only the rows where the customer ID appears in both tables, so each result row has matching customer and order information. This means any customer without an order or any order without a matching customer is excluded. This operation is useful when you want to focus only on the overlapping records between the two datasets. Using the Polars library, we can perform a left join between the customers and orders tables based on the customer ID. A left join keeps every row from the customers table, even when there is no matching row in the orders table. In those cases, the order-related fields in the result will be null. This is useful when you want to preserve all customer records while adding order information only where it exists. An outer join between the customers and orders tables uses the customer ID to combine all rows from both tables into one result. Every customer and every order appears, even if they do not match with each other. When there is no corresponding row in the other table, the missing information is filled in with null values. This type of join is useful when you need a complete view of both datasets, regardless of whether every customer has an order or every order has a matching customer. In this example, we use the Polars library to perform a semi-join between the customers and orders tables. A semi-join keeps only the rows from the customers table where there is at least one matching order, based on the customer identifier. The result is a filtered customers table that includes only customers who have placed at least one order. This lets us quickly see which customers are actually associated with orders, without bringing in the order details themselves. In this example, we use the Polars library to perform an anti-join that finds customers who have no orders. We call the join operation on the customer's data, use the orders data as the table to join with, and match rows based on the customer ID. By setting the join type to anti, the operation removes any customers who have matching entries in the orders table. The result is a list of only those customers who do not have any corresponding orders. The code prints the results of several join operations so you can compare how they affect the data. It first shows the inner join, which keeps only rows where customer identifiers match in both tables. Then it displays the left join, which keeps all customers and any matching orders, followed by the outer join, which keeps all rows from both tables and fills in missing matches with nulls. Next, it prints the semi-join, listing only customers who have at least one order. And finally, the anti-join, listing customers with no matching orders. Together, these outputs illustrate the different ways join types include or exclude rows from the two tables. This script uses the Polars library to demonstrate different types of joins between two small tables, customers and orders. It first shows the original tables, then performs an inner join to keep only customers who have matching orders, such as Bob and Carol. A left join keeps all customers and adds order details when they exist, so Alice appears without order information. An outer join includes every customer and every order, filling in missing values, which reveals both Alice and an unmatched order for a fourth customer. A semi-join returns only customers who have at least one order, while an anti-join returns customers with no orders, identifying Alice as the only one without a purchase. Key-based joins. As you move from simple joins to more complex data integration, choosing and managing join keys becomes essential. Most datasets do not have a single perfect identifier, so you must select columns that uniquely identify records and match them across tables. For example, a retail team might join sales, product, and calendar data using product IDs and dates, while a university might combine enrollment and schedules using student IDs, course codes, and terms. These join keys act as bridges that tell the system how rows relate, and it is your responsibility to define them clearly so the final dataset accurately reflects the real-world relationships. When working with joins, it is important to focus on the logical keys that link tables, not just on matching column names. The same key may have different labels in different tables, such as a customer identifier being called customer ID in one table and client key in another. In some cases, you need composite keys where a combination of columns like country and city or store ID and transaction date uniquely defines the relationship. Keeping these key semantics consistent ensures that your joins preserve the intent of the original analysis, even when the syntax or column names change across datasets or tools. When choosing join keys, you must understand their data quality and what they actually represent before using them in a pipeline. In many domains, a single identifier is not enough, and you may need to combine it with information like dates to avoid merging unrelated records. These choices, such as pairing patient IDs with encounter dates or currency codes with effective dates, reflect assumptions about uniqueness and timing. By being clear about what each join key means, you reduce data errors and make your pipelines easier to validate and maintain. Python code, key-based joins. This section shows how to perform key-based joins in Polars, including joins that use renamed columns and joins that rely on multiple columns as a composite key. It focuses on linking sales fact data to related product and calendar tables using clear and explicit join keys. The material also contrasts the familiar way of thinking about multi-column joins in Pandas with the Polars approach, highlighting how similar concepts are expressed with Polars syntax. Before you can use the Polars library in Python, you must install it with the pit package manager. Installing Polars makes the library available in your environment so you can create and work with DataFrames. This setup is necessary for performing operations, such as key-based joins in the later code. In this script, we use the Polars library to create and work with DataFrames. Polars is designed for high performance and efficiency, especially when handling large datasets, which makes it well-suited for data processing. Here, we rely on Polars to perform key-based joins between tables, so we can merge data using specific columns as the linking keys. We begin by creating a Polars DataFrame to store our sales data, with columns for store IDs, product IDs, sale dates, and units sold. The store and product identifiers let us connect this sales data to other tables that hold more details about each store or product. The sale date column records when each transaction happened. This structure is important because it allows us to join the sales data with related product and date tables for further analysis. We are building a product dimension table in Polars that includes a client key column as the unique identifier for each product. The table also has a product name column that stores names like widget or gadget, and a category column that groups products into areas such as tools or electronics. Using this structure, we can later join the product table with other tables by matching on the client key, even if the key column has a different name in the sales data. We use Polars to build a simple calendar table as a data frame with two key pieces of information for each date. One column stores the calendar date as a string, and the other stores the corresponding day name, such as Monday or Tuesday. This structure lets us later join the calendar table with other datasets on the date, so we can easily add day-specific details to our analyses. We are using Polars to join two data tables, one with sales data and one with product information. The join uses matching keys, but the key column is named Product ID in the sales table and Client Key in the products table. This is a left join, so every row from the sales table is kept, and matching product details are added when the keys line up. If a sales row has no matching key in the products table, it still appears in the result, but the product fields are left empty. We use Polars to join two tables, one with sales data from a previous join and another that serves as a calendar with date information. The join matches the sale date in the sales table with the calendar date in the calendar table. We perform a left join so that all sales records are kept, even if some do not have a matching calendar entry. When a match exists, the corresponding calendar information is added to the sales row. This enriches the sales data with additional date-related attributes from the calendar. The code takes the final joined data table and uses a selection operation to keep only the most relevant columns. These include the store and product identifiers, the product name, the sale date, the day of the week, and the number of units sold. It then prints this filtered view so you can see how the original sales records have been enriched with additional product and calendar details. This script shows how to perform key-based joins in the Polars library using sales, product, and calendar data. It first creates a sales table with store, product, and date identifiers, then a product table with a differently named product key and a calendar table keyed by date. Sales data is joined with the product table by matching the product identifier to the client key, producing a combined table that adds product details to each sale. The result is then joined with the calendar table on the sale date to add the day of the week. Finally, selected columns are printed to display store and product identifiers, product names, sale dates, day names, and units sold, illustrating how Polars efficiently handles joins with renamed and composite keys in a way comparable to Pandas operations. Handling duplicate and missing keys. When you move from simple examples to real-world data joins, handling duplicate and missing keys becomes critical. In practice, identifiers like customer or product codes may appear multiple times or be absent, and this directly affects the join results. A library such as Polars will faithfully apply the join logic to these irregularities, so you must understand how they change your output. Based on this understanding, you may need pre-processing steps like aggregation or filtering to make the join data match your analysis goals. When you join tables that both contain duplicate keys, you create a many-to-many relationship that can greatly increase the number of rows in the result. For example, if the same customer appears multiple times in both a campaign table and a follow-up calls table, joining on customer ID will produce a row for every possible pairing of those records. This behavior can be useful for modeling interactions, but it may distort your data and slow processing if it happens unintentionally. In Polars, joins keep all such combinations, so you often need to aggregate data to unique keys or ensure keys are unique in advance, especially in sensitive areas like finance or healthcare, where duplicates may signal data quality problems. Missing keys in join operations control which rows are kept and which end up with incomplete information. For example, if some shipments do not have warehouse identifiers, an inner join will drop those shipments, which works well when you only want fully matched completed deliveries. A left join, in contrast, keeps all shipments and simply marks missing warehouse details, giving a more complete picture of the data. In Polars, missing keys never match anything, not even other missing values, so they behave as non-joinable keys. This means you must deliberately choose whether to fill in, filter out, or explicitly interpret these gaps in your analysis. Python code. Handling duplicate and missing keys. Explain how joins work in Polars when there are duplicate and missing keys, focusing on how these situations affect the resulting data. Show that many-to-many joins, where both tables have repeated key values, can greatly increase the number of rows in the output. Also clarify how rows with missing keys are treated differently depending on the join type, such as whether they are kept, matched with nulls, or dropped entirely. Emphasize these behaviors so learners understand how join choices impact row counts and the presence of unmatched data. The line with the exclamation mark runs a command that installs the Polars and PyArrow libraries, while hiding the usual installation messages. This prepares the environment so the code can use Polars for fast DataFrame operations and PyArrow for working with columnar data formats. Having these libraries installed is necessary for the code to handle data efficiently and run correctly. We begin by importing the Polars library, which is built for fast and efficient work with DataFrames. It is especially helpful when working with large datasets or when performance is very important, because it can process data more quickly than some other tools. By using Polars, we prepare our environment to handle complex data manipulations and joins in an efficient way. We begin by creating a customer's dataset using the Polars library with two columns, customer identifier and state. The customer identifier column holds unique values for each customer, labeled 1, 2, and 3. The state column records the state for each customer using the values New York, California, and Texas. This simple, structured layout makes it easy to store, access, and later join customer information with other related data. We create a data frame called orders using the Polars library with two columns, order ID and customer ID. The order ID column holds 4 order numbers, 101, 102, 103, and 104. The customer ID column has some repeated values and one missing value. Customer 1 appears twice. Customer 2 appears once, and one entry is missing. This simple setup is designed to show how join operations behave when there are duplicate keys and missing customer IDs. In this example, we use the Polars library to perform an inner join between two data frames called customers and orders, matching them on the customer ID column. An inner join keeps only the rows where the customer ID appears in both data frames, effectively linking each customer to their corresponding orders. When there are duplicate customer IDs in the orders data, the join produces multiple rows for that customer because each matching pair of customer IDs creates a separate row in the result. This behavior shows how duplicate keys can expand the number of rows in the join data frame. We perform a left join between the customers and orders data using the customer ID as the key, so that every customer is kept in the result. Even if a customer has no matching record in the orders data, their row still appears. In those cases, the order-related fields are filled with null values. This method lets us maintain a complete customer list while still including any available order information. This code performs a right join between the customers and orders datasets using the customer ID as the key. A right join keeps all rows from the orders data even when there is no matching customer record. As a result, every order appears in the output, including those without a corresponding customer. This makes it easy to spot orders that are missing customer information and to identify gaps or inconsistencies in the data relationships. This code performs an inner join between two data tables and prints the result. It first explains that the output will include multiple rows for customer 1 because there are duplicate keys in the data. The inner join keeps only the rows where customer identifiers match in both tables. As a result, any duplicate customer entries in the orders table appear multiple times in the final joined output. We first print a short message to explain that we are about to show the result of a left join, which keeps all customers even if they have no matching orders. Then, we display the joined data, where the customer's information is combined with the orders information. Every customer appears in this result, and customers without orders are still listed, just without matching order details. This clearly demonstrates how a left join handles unmatched customers and makes the behavior of the join easy to see. This code prints the result of a right join between two data tables where all rows from the orders table are kept even when some orders do not have matching customer identifiers. The printed message explains that the output includes every order and points out that some may have missing customer information. After this description, the code prints the joins table itself, showing that orders without matching customers are still present in the result, with their missing keys clearly visible. This script uses the Polars library to show how different join types handle duplicate and missing keys. It builds one data frame of customers with unique identifiers and another of orders that includes repeated and missing customer identifiers. An inner join duplicates rows for customers that appear multiple times in the orders. A left join keeps all customers and fills in nulls where there are no matching orders. A right join keeps all orders, including those with missing customer identifiers, and shows nulls for customers that do not match. Overall, it illustrates how many-to-many relationships can increase row counts and how each join type treats missing keys. Polars data reshaping. Wide to long pivoting. Wide to long pivoting transforms data that has many measurement columns into a format where those measurements are stacked in a single value column, with another column indicating the measurement type or category. In a wide layout, each entity, such as a customer, has separate columns for different conditions or time periods, which can make analysis harder. Converting to a long format turns these columns into rows, making filtering and visualization more straightforward. In Polars, this variable name and value structure is a key approach for reshaping data and is consistent with common practices in other data analysis tools. When a sales table stores each store's revenue in separate columns for different quarters, it becomes harder to compare quarters, plot time series, or calculate growth. Converting this wide layout into a long format, where all revenue values are in one column and another column indicates the quarter, makes analysis much simpler. In this long format, you can easily group by quarter, filter specific periods, and connect the data to visualization tools. The same idea applies in areas like education or healthcare, where multiple measurements can be reorganized into a more manageable, long structure for clearer analysis. In Polars, wide to long pivoting works like melting in other data tools. You keep identifier columns, such as student IDs or dates, unchanged, while turning multiple measurement columns into a single value column plus a companion column that records which variable each value came from. This reshaping makes it easier to filter variables, compute metrics, and later pivot back to a wide format if needed. By mastering this transformation, you can build flexible data pipelines that adapt efficiently to new data types or time periods. Python code, wide to long pivoting. This example shows how to pivot data from a wide format to a long format using a Polars DataFrame. We start with simple store revenue data, where each column holds revenue for a different period. By reshaping it to long format, we turn those period columns into rows, creating a tidy table with one row per store and period combination. Comparing the original wide table with the long tidy table makes it clear how this transformation organizes the data for easier analysis. The line with the exclamation mark runs a command that installs the Polars and PyArrow libraries in the background while hiding the usual installation messages. This ensures the required libraries are available for the script, especially in environments where they may not already be installed. Using the quiet option keeps the output clean so you can focus on the script's results instead of the installation details. We begin by importing the Polars library, which is built for fast and efficient work with DataFrames. It is especially helpful when dealing with large datasets or when performance matters. Using Polars prepares our environment for powerful data manipulation tasks. In this script, we will rely on it to transform data, including pivoting from a wide format to a long format. We use the Polars library to create a data frame in wide format, where each row is a store and each column is revenue for a specific quarter. In this example, we include two stores called North and South. For each store, we record their revenue for the first and second quarters in US dollars. This structure makes it easy to compare how each store performs across different quarters. We begin by displaying the original wide format data frame, where each store's quarterly revenue appears in its own column. This initial view serves as a reference for how the data is currently organized. Seeing the wide layout first makes it easier to understand and compare once we convert the data into a long format. We use the melt function in Polars to convert a data frame from wide format to long format. The store column is treated as an identifier, so it stays the same for each row. The revenue for quarter 1 and quarter 2 columns are selected as the values to be turned into rows. We then create a new column called quarter to hold the original column names, and another column called revenue in dollars to hold their values. This reshaping makes the data easier to analyze by quarter. We now look at the long format data frame, where each row shows a single store and its revenue for one specific quarter. This transformed layout is helpful because it follows tidy data principles, with each observation in its own row and each variable in its own column. Using this structure makes the data easier to analyze, process, and visualize in later steps. This script shows how to convert a wide data table into a long format using the Polars library. It starts with quarterly revenue data for two stores, North and South, where each quarter's revenue is in a separate column. The script first displays this wide table, then uses a melt operation to pivot the quarterly columns into rows. The final result is a tidy table with one row per store and quarter, and three columns: store, quarter, and revenue in dollars. This long format is more convenient for tasks like time series analysis and plotting. Column melting basics. Column melting in Polars converts a wide dataset into a long, tidy format by stacking multiple measurement columns into two new columns, one that stores the original column names and one that stores their values. Identifier columns, such as student ID or school, are kept as they are and repeated for each resulting row. For example, separate columns for math, science, and history scores become a single subject column and a single score column. So each row now represents one student and one subject. This long format makes it easier to filter, group, and aggregate data across different subjects. When using column melting in Polars, you first separate identifier columns from value columns. Identifier columns, such as customer IDs or dates, remain unchanged and are repeated for each melted entry. Value columns, which hold similar types of data spread across multiple fields, are combined into a pair of new columns, often called something like variable and value. For example, weekday and weekend sales columns can be melted into a single period column and a single sales column, creating a tidy format that many tools expect. Column melting is a technique used to convert wide datasets into a long format that is better suited for analysis. Instead of having many separate columns for different years or metrics, such as cases, hospitalizations, and deaths, melting turns them into a single column for the year and a single column for the metric. This structure makes it easier to analyze trends over time, compare values across years, and feed the data into plotting tools. Because of this flexibility, column melting is especially important in fields like public health, finance, and marketing, where complex workflows and advanced data manipulation are common. Python code, column melting basics. This section explains how to perform a basic column melt in Polars, converting data from a wide format to a long format. It clarifies the difference between identifier columns, which stay fixed and describe each row, and value columns, which are unpivoted into key value pairs. The goal is to help you see how the original wide table compares to the resulting long table, and to understand how the structure of the data changes during this transformation. The line with the exclamation mark runs a command that installs the Polars and PyArrow libraries, while hiding the usual installation messages. This prepares the environment for working with DataFrames using Polars, a high-performance alternative to Pandas. PyArrow is installed alongside Polars to support efficient data processing and storage. We begin by importing the Polars library, which is designed for efficient DataFrame operations. Polars is chosen because it is fast and well-suited for working with large datasets. With this library available, we can perform various data manipulations, including converting data from a wide format to a long format. This type of transformation is a common and important step in many data analysis workflows. We create a data frame using the Polars library, which is designed for efficient data handling similar to Pandas. The data is in a wide format, where each row represents a student and each subject score is stored in a separate column. We include a student ID column for 2 students, a school column indicating North High and South High, and columns for math, science, and history scores. This wide layout lets us view each student's performance across all subjects in a single row, which is useful before converting the data into a long format for other types of analysis. We begin by printing a short message to explain that we are about to display the original wide data frame. This table shows each student's ID, their school, and separate columns for their math, science, and history scores. Presenting this wide format first gives us a clear reference for how the data is currently organized. It also sets the stage for understanding the transformation into a different format that happens later in the script. we use the melt operation in Polars to reshape the data frame from wide to long format. The identifier columns, student ID and school, stay the same, while the score columns for math, science, and history are combined into a single column. We name the new column that stores the original subject names as subject, and the column that stores their values as score. This transformation makes the data easier to analyze or visualize by subject and score. We now display the melted long data frame, which contains the subject and score columns. This view shows how the original wide data has been reorganized so that each subject and its corresponding score appear in separate rows. Printing the data frame to the console lets us clearly see the result of this transformation and compare it with the original wide format. By examining this output, we can verify that the reshaping step worked as intended. This script shows how to convert a wide data table into a long format using the Polars library. It starts with a table that has student IDs, school names, and separate columns for math, science, and history scores. Using the melt function, it reshapes the data so that each row contains a single score along with the corresponding student ID, school, and subject. This long or tidy format is often better for analysis because each variable is in its own column and each observation is in its own row. The script prints both the original wide table and the transformed long table to highlight the structural change. Pivot table equivalence. When moving from a tool with a built-in pivot table to one with more general reshaping tools, it helps to see what a pivot table actually does. A pivot table turns a long list of records into a matrix by choosing what goes in the rows and columns, then aggregating numeric values with operations like sums or averages. Analysts use this to create compact summaries, such as sales by category or grades by semester. In modern data libraries, you achieve the same result by grouping, aggregating, and then reshaping the data, ultimately computing summary values and arranging them into a familiar pivoted layout for reports and dashboards. To build the equivalent of a pivot table, start with data where each row is a single observation, such as a sale or an exam score. Choose one or more columns to group by, like customer segment and quarter, and identify the column that contains the values you want to summarize, such as revenue. Apply aggregation functions to compute summaries for each combination of grouping keys. For example, total revenue per segment per quarter. Finally, reshape the result so that one categorical variable forms the columns and the others define the rows, giving you a two-dimensional view that makes it easy to compare categories, just like a pivot table in a spreadsheet. Pivot table style analyses let you handle complex data by grouping, aggregating, and reshaping information. You can compute statistics like counts or averages for different categories. Then turn those categories into columns to compare them side by side. This approach works across many domains, such as analyzing hospital admissions by department and month, or comparing headcount and salary by job family and location. By viewing pivot tables as a flexible way to group, summarize, and rearrange data, you can support both quick exploration and more formal reporting. Python code, pivot table equivalence. This lesson shows how to reshape long transactional data into a pivot table style summary using Polars. You will see how to group the data, apply aggregations, and then pivot it to form a wide summary matrix. The focus is on comparing the original long format with the pivoted wide output, so you can clearly understand how the transformation changes the structure of the data while preserving the underlying information. The line starting with an exclamation mark is a command used in environments like Jupyter Notebooks to install the Polars and PyArrow libraries. Polars provides efficient tools for working with DataFrames, and PyArrow supports data interchange and storage formats. Installing these libraries is an essential setup step because the rest of the code depends on them for data manipulation and analysis. We begin by importing the Polars library, which is built for fast and efficient work with data tables. It offers tools similar to those in Pandas, but is optimized for performance, especially on large datasets. Using Polars prepares our environment for key data manipulation tasks, such as grouping, aggregating, and pivoting. These operations are essential for transforming raw data and creating useful summaries. We create a dictionary to store sales data in a long format, using 3 keys: region, product, and revenue in dollars. Each key is linked to a list, so the region list repeats north, south, and west. The product list repeats gadget and widget for each region, and the revenue list holds the corresponding sales amounts. This structure organizes each sale as a combination of region, product type, and revenue value. With the data arranged this way, it is ready for further processing and analysis. We begin by turning the data dictionary into a Polars DataFrame so it becomes easy to manipulate and analyze. Using Polars gives us performance advantages for large datasets, similar to Pandas but optimized for speed and memory use. This DataFrame then acts as the base structure for later operations, such as grouping and pivoting the data. We begin by printing the original sales data in its long format to establish a clear reference before making any changes. The data is stored in a Polars DataFrame, which is well suited for working with tabular information. By displaying this DataFrame, we can verify the initial state of the data, including regions, products, and their revenue values. This initial view is important, so we can later compare how the data looks after applying operations such as grouping and pivoting. We first group the sales data by both region and product, so that each subset contains records for a specific region and product combination. Then we aggregate these groups by summing the revenue dollars within each one. This calculation gives us the total revenue for every region and product pair. Finally, we rename this summed value as total revenue to clearly indicate what the numbers represent in the resulting data. This code reshapes the grouped sales data into a pivot table using a Polars pivot operation. It spreads the total revenue values across columns so that each column represents a different product. The region becomes the index, so each row corresponds to a specific region. This layout makes it easy to compare revenue for different products within each region, much like a pivot table in a spreadsheet program. We begin by printing a short message to explain that the next output is a pivot-style revenue summary, so the listener knows what to expect. Then we display the pivoted data, which shows revenue organized by region and product. This layout makes it easy to compare revenue across different regions and products, much like using a pivot table in a spreadsheet. This script shows how to convert long transactional sales data into a pivot table using the Polars library. It starts with a dataset of revenue by region and product, where each row represents one region and product combination. The data is first grouped by region and product to calculate total revenue for each pair. Then it is pivoted so that product categories become columns, creating a wide summary table. When you run the code, you see the original long format followed by this pivoted view, which clearly summarizes revenue for each product in each region. Polars pipeline design, combining joins and transforms. When designing a data pipeline, you often start with several related tables, such as customer records and transaction logs, and join them using shared keys like customer IDs or dates. These joins usually create a wide intermediate dataset that then needs to be reshaped to match your final analysis goals. Planning how each join will feed into later transformations helps keep the pipeline simple and efficient. With this foresight, you avoid redundant joins, awkward data structures, and extra work in later steps. When combining joins and transforms, first picture the final table you want and then work backward to decide which steps you need. For example, if you want one row per customer and columns for each product category's total revenue, you would join transactions with product data to get categories, then join with customer data for demographics, and finally aggregate and pivot to create the summary. For sensor data, you might join device metadata with readings. Then reshape the data into a wide format or a tidy long format to make analysis easier. In all cases, joins give you the full context, and reshaping adjusts the structure for modeling or reporting. When refining data pipelines, you need to think about how your join strategy affects later reshaping steps. The choice between inner, left, or outer joins and the join keys you use determines which rows reach the pivoting stage and how complete the resulting tables are. If you pivot on a categorical variable that is sometimes missing, you may want a join that preserves all categories so the output still includes columns for those missing values. For operations like melting, it can help to keep data in a long format until the final steps. By aligning your join choices with pivoting and other transformations, you build pipelines that are efficient, easy to interpret, and robust to changes in the data. Python code, combining joins and transforms. This lesson will demonstrate how to combine joins and reshaping in Polars using a pipeline style. You will see how to take multiple small tables, join them together step by step, and then reshape the result with a pivot operation. The goal is to produce a clear, final summary table while keeping the example simple and beginner-friendly. By the end, you should understand how joins and pivoting can work together smoothly in a single Polars pipeline. To work with DataFrames using the Polars library in Python, you first need to install Polars with the standard pip install command. This installation step makes the library available in your Python environment. Once installed, you can use Polars to perform efficient data manipulation and analysis. Its features are designed to handle these tasks quickly and effectively. We begin by importing the Polars library so we can work with DataFrames. Polars serves a similar role to Pandas, but is designed to be faster and more efficient, especially for large datasets. By importing it, we gain access to its tools for manipulating and analyzing data. This sets up everything we need for the data operations that follow in the code. We begin by creating a simple customer table in Polars with 2 columns, one for customer IDs and one for their states. The table contains 2 customers labeled with IDs 1 and 2. Each customer is linked to a state using its abbreviation, with one from California and the other from New York. This basic structure lets us associate each customer with geographic information, which can then be used in later data operations and analysis. We begin by creating a products table using Polars with 3 main columns: product ID, category, and price in US dollars. The product ID uniquely identifies each item, while the category describes what type of product it is, such as tools or toys. The price column stores how much each product costs in US currency. This simple structure makes it easy to manage product information and prepares the data for joining with other tables and performing further analysis. We build a transactions table using Polars that connects customers to the products they buy. It includes a customer ID column, a product ID column, and a quantity column showing how many units of each product each customer purchased. With this structure, we can clearly see which customers bought which products and in what amounts. This table serves as the foundation for later analysis and data transformations. We begin by joining the transactions table with the products table using the shared product ID column. This join adds product details such as categories and prices to each transaction. We use a left join so that all transactions are kept even when some products have no matching information. The result is a single, richer dataset that combines both transaction and product data for later analysis and calculations. We enhance the transaction data by adding a new revenue column to the existing table of transaction and product details. Using a column creation method from Polars, we define a revenue in US dollars for each transaction line. This revenue is calculated by multiplying the quantity sold by the product's price in US dollars. The result is a clear measure of total revenue per transaction line, which makes it easier to analyze overall sales performance. We join the enriched transactions data with the customer's data using a left join on the customer ID column. This means every transaction is kept, and matching customer information is added where available. The main goal is to attach each transaction to the customer's state. By doing this, we enhance the transaction records with geographic details from the customer's table. We begin by grouping the data by customer ID and product category so that each customer's purchases are organized within each category. For every group, we then add up the revenue in US dollars to find the total amount spent. Finally, we label this result as total revenue in US dollars to clearly indicate what the summed values represent for each customer and category. We reshape the aggregated data into a wide format by using a pivot operation that turns each product category into its own column and places total revenue values in the cells. The customer ID is used as the index so that each row represents a single customer. We then sort the matrix by customer ID to keep the rows in a clear, logical order. This transformation makes it easier to compare and analyze how each customer's revenue is distributed across different product categories. We now present the final matrix, which captures the combined results of all our joins and transformations. This matrix summarizes revenue data by customer and product category. So each cell reflects the financial contribution of a specific category for a specific customer. By organizing the information in this way, it becomes much easier to interpret and compare revenue across different customers and categories. This script shows how to use polars to reshape and summarize data by combining joins and transformations. It starts with customer, product, and transaction tables, then joins transactions with products to add product details and compute revenue as quantity times price. The enriched transactions are then joined with customers to bring in customer state information. After that, the script aggregates total revenue by customer and product category and pivots the result into a matrix. The final output is a compact table that shows how much each customer spent in each product category, illustrating Polars' strengths for data manipulation and summarization. LazyFrame pipeline patterns. Instead of thinking of data work as separate commands, think of it as a pipeline of transformations. A LazyFrame is a blueprint that describes how your final dataset is built from raw sources using joins, filters, and reshaping steps. You define the whole process first, and Polars waits to run it until you request the final result. This delayed execution lets Polars optimize the entire pipeline, streamline operations, reduce redundant work, and improve overall efficiency. When designing data pipelines, it helps to break the workflow into clear stages that mirror your analysis steps. You typically start by ingesting data from multiple sources, then move to a relational stage where you join related datasets, and finally reshape the result to match the needs of downstream users. For example, you might combine sales, product, and regional information into one view and then format it for business dashboards or statistical models. By chaining these transformations with lazy evaluation in Polars, you maintain a clear transformation story while allowing the system to optimize the entire process efficiently. When building data pipelines with Polars, it is important to keep all transformations inside the lazy computation graph instead of creating intermediate results too early. You can still validate your logic by using selective sampling or small test runs while preserving this lazy structure. For example, joining healthcare data, reshaping it, and aggregating by hospital should all stay in a single lazy pipeline. This lets Polars optimize the work by removing unnecessary steps and pushing filters earlier, which makes the pipeline faster, more efficient, and easier to manage and compare. Validating pipeline equivalence. When moving a workflow from Pandas to Polars, the main goal is to confirm that the new pipeline produces equivalent analytically results. Start by clearly defining what counts as the same result for your project, such as identical values and ordering, or just matching aggregated metrics. For example, a finance team might require that customer totals and key indicators match, even if the row order changes. Setting these criteria in advance helps you design a focused validation process that protects data correctness and supports reliable decisions. Begin by clearly defining what it means for your Pandas and Polars results to be equivalent. Then, validate the Polars pipeline in stages using small, controlled test datasets. Design test cases that stress the joins and reshaping steps, including situations with multiple orders and missing values, and run both workflows on the same inputs. Compare their outputs using key metrics such as column summaries and group aggregates, and confirm that important measures like conversion rates and trends match. Working with smaller datasets at first makes it easier to spot and correct any discrepancies before you move on to larger real-world data. After your pipeline works on test cases, validate it with real or near-real production data by comparing high-level statistics instead of individual rows, especially for large datasets. For example, you might check that daily totals and averages, such as shipment counts and delivery times, stay consistent when moving from one data processing tool to another. Continue to monitor the pipeline over time and revalidate it whenever data schemas change or new transformations are introduced. This ongoing validation helps ensure the new Polars-based pipeline remains accurate and aligned with the original analytical goals while taking advantage of better speed and scalability. Python code. Validating pipeline equivalence. This lesson focuses on checking that data processing pipelines built with Pandas and Polars produce equivalent results. You will learn how to define simple metrics and clear equivalence criteria, then use them to compare aggregated outputs from both tools. Using a small customer order dataset, you will validate that joins and reshaping steps behave the same way in each pipeline. The goal is to build confidence that the two implementations are consistent and interchangeable for the same data tasks. A line that begins with an exclamation mark is a command used to install the Polars and Pandas libraries. It is commonly run in environments such as Jupyter Notebooks to make sure both libraries are available. This setup step provides the tools needed to work with DataFrames in each library and later compare how their features and performance differ in the code. We begin by importing the Pandas library for data manipulation and analysis, and then import the Polars library, another data processing tool designed for high performance. These imports prepare our environment to work with data using both libraries. Having both available lets us handle data efficiently and later compare how Pandas and Polars differ in their features and performance. We begin by creating two small Pandas datasets to model our scenario. One dataset stores customer information, including a customer ID and the region where each customer is located. The other dataset stores order information, including an order ID, the customer ID linked to that order, and the revenue in US dollars. Together, these datasets let us simulate customer orders and connect each order to the customer's region, providing a simple foundation for later data processing and analysis. We begin by joining the orders data with the customer's data using a left join on the customer ID so that each order is matched with its customer details. After this merge, we group the combined data by region to analyze each region separately. For each region, we compute the total revenue in US dollars. Finally, we sort the regions so the results appear in a clear, consistent order that is easy to compare with other data sets. We begin by converting the customer's data from a Pandas data frame into a Polars data frame, so we can use Polars for our analysis. We then perform the same conversion for the orders data. With both datasets in Polars format, we can apply Polars methods to process them efficiently. The goal is to reproduce the operations we previously did with Pandas, but now using Polars and its performance advantages. Using Polars, we first join the orders and customers data on the customer ID, performing the same kind of left join used in Pandas so that every order is linked to its customer. We then group this join data by region, just as we would with a group by operation in Pandas. For each region, we calculate total revenue in US dollars by summing the values. Finally, we sort the regions so the output is in a consistent order for comparison with the Pandas results. We define equivalence by comparing total revenue for each region, rather than relying on the order of rows, so that sorting differences do not affect the comparison. To do this, we focus on the aggregated revenue results by region. We then print the total revenue per region produced by the Pandas pipeline, which gives us a clear view of the computed values. This printed output serves as a reference for visually checking and comparing the results against those from the Polars pipeline. We first convert the Polars result into a Pandas data frame, so it is easier to compare directly with the Pandas output. After this conversion, we print the Polars results showing the total revenue by region. We format the display without row indices to keep the comparison clean and focused on the values themselves. We first reset the index of the Pandas result so it starts from 0 and remove any old index, which makes it easier to compare with the Polars result. Then we convert the Polars output into a Pandas data frame and reset its index in the same way, so both results share the same structure. After that, we compare the two data frames by checking whether their region and revenue columns match when sorted. Finally, we report whether the two pipelines produce the same regional revenue, showing if the outputs from both libraries are equivalent. This script shows how to check that data processing pipelines built with Pandas and Polars produce equivalent results. It creates small customer and order datasets, then uses Pandas to merge them by customer ID, and compute total revenue by region. The Polars pipeline repeats the same join and aggregation steps. Both pipelines then output regional revenue totals sorted by region name. Finally, the script compares these outputs, ignoring row order, to confirm that the numerical results for each region match in both frameworks. In this lecture, you learned to implement Polars joins that replicate common Pandas merge and join patterns across multiple tables. Apply Polars reshaping operations such as pivot and melt to reproduce Pandas pivot table and stack or unstack behavior. And design an end-to-end Polars pipeline that combines joins and reshaping to match the output of an existing Pandas workflow. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.